Sorry if you're watching the recording. We're already here. Oh, look, we started lesson 5. I said some stuff. It was profound. My apologies. So now here we are. V equals the square root of GME over R. Now I can just plug in these values. This is going to equal the square root of 6.67 times 10 to the negative 11 times the mass of the Earth, 5 point something, times 10 to the something, divided by R, 26,380,000. And we get that the velocity for that object in orbit, for it to maintain a constant circular orbit, has to be what? At least 2. That is technically correct.
I'll say at least.
It's like Price is Right. It's got to be at least 1. You want to be close without going over, right? What's that value? Zach, what'd you get? 3,888 meters per second. Can someone verify that? A couple people verified. Okay, cool. Comments, questions, concerns about what we just dealt with? Okay, there's an interesting little result here. Flip the page. We found that, so the expression that I derived on the previous page, that V is equal to the square root of GM over R, is the expression for an object in orbital speed independent of the mass. The only thing it depends on is the orbital radius and the central mass. Okay, fun story. I was hanging out, I can't even remember what night it was. I think it was like Thursday night last week. My daughter had gone to bed. My wife was watching Chicago Med. I was playing Stardew Valley, and I'm sitting at my computer, and a buddy messages me, a buddy who is like obsessed with Kerbal. Hands up if you've heard of Kerbal Space Program. Okay, Kerbal Space Program is one of the most accurate space launch and orbiting simulators. If you've got some money kicking around and you're bored and you really want to blow your mind, Kerbal Space Program is a fantastic program. And I got an email out of the blue from a buddy of mine. He's like, hey, so if I wanted to orbit a planet 1 foot off the surface of the planet, how would I do it? And I said, I'm literally teaching this on Monday. That's the expression that you need. It was fun how life just kind of happened. So, there is a proof that we are going to take a look at here. Acceleration for an object in circular motion is equal to what? Yeah. Okay, A equals what? For an object in circular motion, velocity squared over the radius. Cool. And for an object in orbit, we've established that the velocity is the square root of GM over R, which gives us this result. The result is that A equals V squared over R, so that's going to give us GM over R squared. GM over R squared is equal to what? You've seen this before. No. GM over R squared is a little g. That tells us that for an object in orbit, little g equals A. So because little a equals g, and that little g showed up when we were looking at objects in free fall, projectile motion, that tells us that for you to be in orbit, you must be in a constant state of free fall. So effectively what's happening is this. You are constantly trying to fall to the surface of Earth when you're in orbit. You just keep missing because you're bad at it. Okay? That's effectively what that means. You're going too fast to actually, that's what this is demonstrating down here. You're going too fast to fall to the surface. You're still in projectile motion. That's still what's happening here. You just keep missing when you are in orbit. So if you hate the feeling of falling, for those of us who hate the feeling of falling, that awkward kind of Yeah, you know what it feels like in your stomach. You've never done it for very long, because even when you're falling like on the elevator, that's not a very far fall. But if you've been falling for any length of time, you tense up because you get that. That's what astronauts feel constantly, because they are constantly in a state of free fall, which is often why when astronauts go to space for the first time, they vomit, because they're not used, because they don't necessarily like that feeling, but they feel like that constantly. That is the constant state of their body, which is pretty cool.
Yeah, I thought no. You could like cover around pretty much anything on the.
Sorry? Yes. Oh, yes.
Like
So let's flip the page.
I around in a water.
Let's flip the page. The fact that an object in orbit is in continuous free fall is interesting, whether you believe it or not. It means that things in orbit are always falling towards the Earth, even if they never get there. It explains why astronauts seem to float around in the space shuttle. Both the passengers and the ship are in free fall together, falling at the same rate. Therefore, the ship cannot exert a normal force on the passenger. They experience what we call apparent weightlessness. It means that astronauts, like I've said before, continuously experience the physiological feeling of falling. I mean, your body adapts to it, but if you don't like what that feels like, I would suggest you don't go to space. Okay, you want an example that is totally ridiculous. Looney Tunes. Hands up if you ever watched Looney Tunes. Okay? Classic example, you throw something in one direction around the Earth, you wait a little while, it comes back at you from the other side. We've seen this in cartoons, yes? Animaniacs do it. The Looney Tunes do it. We're going to do it. You are standing in the field. You kick a football opposite direction from the uprights, and you want to score a reverse field goal. You want the ball to come back at you through the uprights after having traveled a circular path around the Earth. Okay? There's going to be some problems here. First of all, the Earth's not perfectly smooth. There's mountains in the way. Assuming those aren't there, how fast is the football going to have to go to make this happen? Okay? Here we go. At what speed does the football move to kick it in the opposite direction, have it come around the other side of the Earth, and go through the uprights? The minimum speed we've already established for an object in orbit is v is equal to the square root of gm over r. That would be a bad idea. I'm not going to add it, but if you want to add it, the speed for an object in orbit, you want to toss it on the back? Call it what it is, the speed for an object in orbit, but that v is equal to the square root of gm over r. It's useful. I'll wait for a little bit while those of you who choose to add it. That's certainly not a bad thing to put on there. We can fill it in now, though. We want the square root of 6.67 times 10 to the negative 11. The mass of the Earth, 5.98 times 10 to the 24. This thing is skimming above the surface, so we're going to go start with the 6,380,000 meters. How tall are the uprights? How high off the ground do you think this thing's going to have to go? More than 2 meters. It's like at least it's like 3 or 4 meters. Let's say
4.
Let's say 4. So instead of 6,380,000, we're going 6,380,004.
Is there a point of that, or is it?
Basically not, but we're going to do it anyway. We're going to get what velocity? How fast does that football have to be moving? Yeah, you're going to run that number again. You're definitely going to want to run that number again. I'm just going to... Speed of sound. Hold on. I just need another number here. Yeah. Okay. Yes.
I don't know if 7,906.
Sorry?
That's 7,906.8. Whenever you see flames.
7,906.8 meters per second. Okay. That is the speed at which, and that's the same thing I got. Can someone verify that Zach and I are correct? Actually, you got the same thing? Okay. Okay, so just so we're clear, I'm going to convert that to kilometers per hour just for fun. Multiply that by 3.6, give us 28,464.5 kilometers per hour. This is 20 times the speed of sound. Just so we're clear. Sucker's moving. Which means for a regular football does not have the structural integrity to survive this. The rubber on the football would heat up, the thing would melt into a dust. Okay? So we're assuming we could have a steel football, but then kicking it's going to be a bit of bitch.
But I mean, you know
it is what it is.
I don't think you'll have any.
It's true. So at this point, we need a cannon. Okay? We need a cannon to shoot this object. Okay? This thing has to be traveling at 20 times the speed of sound. Another piece that's kind of interesting, how long does it take to do this? We have another expression for the velocity of an object in uniform circular motion. What is the other expression that we have for the velocity of an object in uniform circular motion? No, velocity. V equals 2 pi r over big T. Big T is the period, the amount of time it takes an object to circle something once, which is exactly what we want our football to do. We want our football to go around the planet once. Okay? So, big T is going to equal 2 pi r, the distance around the planet, divided by V. So let's fill this thing in. We're going to have 2 times pi times 6,380,004 divided by 7,900, 6.8 equal T. How long does that take? Oh, that shouldn't be 40. That should be that should be 04. Oh.
5,069.
Sorry, one more time.
5,069.9.
So basically 5,070. 5,070 what? What are the units on that? Seconds. Okay, I want you to convert that to hours. No, that's minutes. Divide by seconds divided by 60 is minutes. Divide by 60 again. 1 point what? 1.4 hours, which is 1 hour and 25 minutes, give or take. So that cartoon just got a lot longer. Game's over. If you do this on the opening play, half hour after time expires, that comes through. It comes through the uprights at 20 times the speed of sound. Okay? So obviously this isn't going to work because there's objects in the way. It's also the other reason it's not possible to orbit the Earth's surface in this manner. Air resistance is what's going to disintegrate the ball. On the moon, this is possible because the moon has no atmosphere.
Have you ever tried it?
The closest they got was someone smuggled golf ball in the golf club up there. I think it was like the second lunar landing. They were playing golf on the moon. It might have been the first, but I'm pretty sure it was the second. It's possible on the moon because the moon has no atmosphere. Earth has atmosphere. This would be problematic. The football would vaporize. Even moon's pretty big.
How long does it take?
I don't know. Well, the moon has a radius of 1,740 kilometers. Actually, fun fact, the moon and Mars are roughly the same size.
Oh, Mars is tiny.
Yeah, Mars is pretty small.
So Mars still has
Mars is a little bit bigger than the moon, but not much. Okay, flip the page. We're going to do one more example. Using a really... we're going to come up with a very interesting result. Very interesting result. Okay. So, here's the question. The entirety of the question is going to be summed up like this. It takes 300 minutes for a satellite to orbit the Earth. How high above the Earth is it? That's all we're given. Okay? We're going to need a few things. Let's draw the picture first. There's our Earth. Somewhere out here, we have a satellite in orbit. Okay, I'm going to add the circular nature of its orbit in there. The question says, how high above the Earth? None of the formulas that we deal with take that into account. All the formulas that we deal with consider what? More specific. One word is not going to solve the answer to my question. Okay, the radius of the Earth. So this distance needs to be included. This is what we're looking for. This is the value we want. We cannot ignore this. This value is 6,380,000 meters. We want X. So, there's a bunch of things that we're going to have to take into account here. The object is in orbit. So what is the implication there? Uniform circular motion implies constant v. Okay, so we got a couple pieces there. So I'm just going to start writing out. You see orbit, you think uniform circular motion, you immediately write down two things. F net C equals MAC. A equals V squared over R. They've given us something. What have they given? What's the only piece of information they've given us? The time. Okay, they gave us the time in minutes. We don't want time in minutes. We want time in seconds. We're going to multiply that by 60 right away. 60 times, or 6 times 3 is 18, and then we're going to add 3 zeros to it. Thank you. 18,000 seconds. So all they've given us is time. So we're going to have to connect these expressions with an expression involving time. What expression do we have that involves the velocity of an object and time? V is equal to 2 pi r over t. And the only other expression that we're going to need is what? We need a force acting on our object. The only force acting on our object is gravity. So we're going to need the universal gravitational. I'm just going to put it right here. Fg equals big G, big M, little m over r squared. So we're going to use these four equations to give us an awesome result. Here we go. We're going to start with this, and I'm going to put it right here. FNC equals MAC. This expression here is my net force. And this expression here is my acceleration. So we're going to get, keep going in black, big G, big M, little m over r squared equals mv squared over r. First thing we're going to do is what? Not yet. We're going to cancel one of the r's. I heard that from the back. And we're going to cancel out the little m's. So we're going to get gm over r is equal to v squared. Now, the suggestion that I heard, but I can't remember who it was from, is what we're going to do next. Suggest it again, whoever you were. Yeah, we don't have a velocity. We just have the time it takes to orbit. So this expression is going to go in here for v. And we're going to get that gm over r is going to be equal to, in brackets, 2 pi r over big T squared. Okay, there are two paths we can take here, depending on the result we want. A fun one can take us that way. We'll do that one here in a second. To actually solve the problem, we got to go this way. What's my next step to solving this problem? What are we looking for? We're looking for R. There's an R buried in there, and there's an R down there. Don't plug your values in yet. It's going to get gross. The first thing we're going to do is when I've got a bunch of things multiplied together, and I've got an exponent outside, what can I do with that exponent? Do not root, because then I'm burying this R inside a root. That is a bad idea. I've got a bunch of things multiplied together, all to a power. So because all I've got in here is multiplication and division, this exponent, if we remember our exponent laws, can go onto everything inside those brackets. So I'm going to get this expression here. Gonna go, this is gonna get weird and gross, but that's okay. GM over R equals 4 pi squared R squared over T squared. To isolate for R, I'm going to multiply this R up, and I'm going to multiply this T squared up, and I'm going to divide both sides by 4 pi squared. Okay? So I'm going to get that R squared, keep this going, I'll go red, I'm going to go this way again. I'm going to get that R cubed is equal to GM T squared over 4 pi squared. And then I can take the cube root of both sides. So now is when we're going to shove our values in here. No, do not put this on your formula sheet. Well, I mean, do what you want with your formula sheet. But this is not the useful result. The one that I'm giving you down here is the useful result. 6.67 times 10 to the negative 11. 5.98 times 10 to the 24. Big T squared is 18,000 squared divided by 4 pi squared. I'll tell you what this value is. You can verify it for me if you want. But the value that I found was, I'll just read it this way, 14848095.9 meters. That is the distance from what to what? That is the distance from the satellite to the center of Earth. We don't want that. So what do I have to do to get x? X is going to be equal to 14848095.9 minus 6,380,000, giving us a value for x of 8,468,096 meters. Which means we could fit another Earth between the Earth and satellite. Oh, that's not true. I lied. Oh, don't ignore what I just said. Oh, boy. Wow. Delete off. Get your act together. Ignore what I just said. No, because this would have to be 12 million. I've got the difference between the radius and the diameter for a second. Ignore what I just said. Oh, boy. That was bad. Okay, this is our result, though. Yeah, but that's not fun. Ignore that. Okay, we cool with the procedure. We started with we were given two pieces of information: the time it took to orbit and the fact that it was in orbit, and everything else fell down. This is the way things are going to be posed to you at some point in the future. This is what you're going to have to reason your way through. Here's the cool result I mentioned earlier. By distributing this thing in here, we get a thing that looks like this. We're going to go GM over R equals 4 pi R squared over T squared, which I also have here, but that's okay. We're going this way. Pi squared. Ooh, pi squared. I'm going to multiply my r up. I'm going to divide my 4 pi squared down. We're going to leave the t squared where it is. So we're going to get that r cubed over t squared is equal to gm over 4 pi squared. This is a constant because g is 6.67 times 10 to the negative 11. The mass of our planet is 5. Well, in this case, for our planet, this is constant for every body in the universe. It's going to be a different constant for every body, but for Earth, it's 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by 4 pi squared. That's equal to your radius cubed over your time squared. This thing here was developed by I'm going to say Danish. No, that's a lie. A Dutch. He was Dutch. A Dutch physicist and astronomer named Johannes Kepler. Have we heard that name Kepler before? Okay. In what context do we know Kepler? Sorry, Hannah? You studied astronomy back in the day? Solar system, but yeah. We're getting there. Shrink it down. Okay? So Johannes Kepler develops this. That's why we call it. This is called Kepler's law. That the radius that you're wanting to orbit cubed divided by the orbital period squared is equal to gm over 4 pi squared, which is a constant for every body in the universe. That's pretty cool. The sun will have its own constant because obviously the sun has a different mass. But g and 4 pi squared don't change anywhere in the universe. This, Kepler's law, is the thing that I would strongly consider tossing on the back of your formula sheet.
What does that help with?
Well, this tells you, this means you could look at any two objects orbiting anywhere in the universe, or orbiting each other anywhere in the universe, and figure out you can do it a few different ways. The mass of one, based on how long it takes to orbit, and the distance it is orbiting the other object. There's a whole bunch of really cool relationships here. This means we can look out anywhere into the universe, and as long as we can measure how long it takes an object to orbit the other one and its orbital radius, we can find out the mass of the object in the middle. That's really cool. That means we can look out into space and see objects like this is how they discover things like the supermassive black hole at the center of our Milky Way. You can see objects orbiting it, even though there's nothing there. You can't see what's there. There has to be something there. We know how quickly this thing's going around. It doesn't matter. The other beauty of it is it doesn't matter the mass of the object in orbit, because that mass canceled out. So this opened up astronomy and the study of our universe in a way that nothing else had prior to. It's very, very cool. To the point where I could work myself up to tears how cool this is. Okay? Very, hugely profound result, whether or not we can appreciate it. Okay? That I would strongly encourage putting on the back of your formula sheet. That's the end of this lesson. It's the introduction to orbits. We're going to go further and connect the orbits to kinetic and potential energy, and then we're done. It's great. Now we've got, what lesson was this? This was 5. We got 3 more lessons, 6, 7, 8. You betcha. Okay, here, flip the page. Here's what I want you to do. Here's your homework on top of the stuff that I assigned earlier. You're doing 2 to 4, 6, 7, 9, and 10.
I want to finish the one I was working on.
Okay, so there you go. That's all your homework.